Good day everyone, and welcome to where we are putting together solutions in the topic of algebra, sequences and series in the subject of additional mathematics. In this video, we'll be looking at the overview of this section 1 of the syllabus and the 5 years solutions for the questions that came on this topic from the years May 2012 until 2016. Feel free to like the video and add any comments down below so we can create other videos to help you. Don't forget to look at the description down below where we have outlined the entire CSEC Additional Mathematics syllabus so that you can get a better understanding. Let's look at the 4 major topics in CSEC Additional Mathematics. And in this video, we'll be looking at section 1, Algebra, Sequences and Series. This section comes for 15 multiple choice questions out of 45 in paper 1. That's 1/3 of the paper. And for the first 2 questions with 15 marks each, which is 30 marks out of the total of 100 in paper 2. We're following the new syllabus which began in 2021, and this varied slightly from the older syllabus in 2012. Section 1 has been subdivided into 5 parts, which are algebra. Can be subdivided into the 4 operations of algebraic expressions, adding, subtracting, multiplying, dividing them, factorizing polynomials up to the 4th degree, up to x to the 4th, and of course then that will carry us to remainder theorem, factor theorem, and then we can find unknown coefficients. So that's a subset of the first topic, algebra. And for the second, part B, is quadratics. In quadratics, students are expected to be able to complete the square, and there are 3 different ways at least that we can try: the expansion form, memorizing the formulae, or using algebra tiles. And this will lead us to getting the maximum or minimum of the quadratic graphs and the intercepts on both axes, the x and y axes, so that we are able to sketch the quadratic graph. In making such a sketch, the nature of the roots are required, so we need to know the discriminant. That way, we will be able to identify whether there are 2 roots, 1 or none at all. Also, in quadratics, we need to be able to solve reducible equations like x to the 4th plus 6x squared plus 5 by using a proper substitution to convert it to a quadratic. We need to know how to work out the sums and products of the roots of the quadratic equations. And the final part of quadratics, which is similar to CSEC Mathematics, solving 2 equations simultaneously, one being linear and the other being nonlinear. Just like at CSEC Math, the second equation could be a quadratic equation, or as an advancement to the topic in Add Maths, it could be a circle. So we need to know how to handle the circle equation. For part C, inequalities, by using graphical or algebraic means, students should be able to find the range and domain of quadratic inequalities and even rational linear inequalities. Ax plus b divided by cx plus d is greater than 0. For the 4th one, Surds, Indices and Logarithms, students should be able to use the basic operations of add, take away, multiply, and rationalize surds. Students should be able to handle the laws of indices to solve exponential equations, linear or quadratic, to convert from the indices form to the logarithm forms or vice versa, and of course the laws of logarithms. Students should be able to solve logarithm equations and apply logarithms to solve problems such as linear reduction. T is equal to ax to the power b, and we can use logarithms to convert that to a linear form. And the last part of section 1 is part E, sequences and series. And in this, students need to know how to find the nth term in a sequence, that a series is a sum of the sequence terms, APs, arithmetic progression, and geometric progression, GPs, and of course the nth term, the sum to the nth term, and the sum to infinity of these, and the final part to show divergence or convergence of the APs and GPs accordingly. Students have asked that we summarize the major topic so they can identify it easily in order to be able to follow each subtopic by itself. So this table shows us where algebra has been tested from May 2012 to 2015. And if we're studying quadratics, we can look specifically at where they were tested over the 5 years. Inequalities for 3 years, May 2012 to 14. Surds for 4 years, sequences, and functions. And of course, functions have been removed from the syllabus. May 2012, number 1A. The functions f and g are defined by f of x is equal to x cubed plus 1 for the range 0 less than or equal to x, which is less than or equal to 3. And the second function g of x is equal to x plus 5 for the range that x are real numbers. Recognizing that this is a functions question, this topic was in the old syllabus and it has been removed from the new one, but we'll show the solution anyhow because it supports our CSEC mathematics and strengthens the students' concepts. So part 1, determine the composition function g f of x. So if we have the composition function g f of x, the first thing we do, we want to solve which function is working on x or on the domain elements first. It will be f. So we want to find f of x. So let's write that. F of x is equal to x cubed plus 1. And there's no substitution, that's all we know. So what that means, instead of writing g f of x, we're going to replace f of x by x cubed plus 1. So we really want to find g of x cubed plus 1. So let's write the formula. G of x is equal to x plus 5. And we want to find g of x cubed plus 1. So we're replacing the x by this new brackets. So that will be x cubed plus 1 plus 5. And that's a simple solution. G of x cubed plus 1 is equal to x cubed plus 1 plus 5 is 6. So the composite function g f of x is equal to x cubed plus 6. Part 2. State the range of g f of x. So we know the domain of f of x is from 0 is less than or equal to x, which is less than or equal to 3. Which means if we're considering the integers alone, but of course there are decimals in between there, the smallest will be 0, 1, 2, and the largest being 3. If we take the smallest and largest values of f and substitute it into the composite function g f of x, that will give us our minimum and maximum. 0 cubed plus 6 is less than or equal to g f of x, which is less than or equal to 3 cubed plus 6. Because let's recall in part 1, we got the composite function to be x cubed plus 6. And 0 cubed is 0 plus 6 is 6. So 6 is less than or equal to g f of x. And 3 cubed, it's 27. 2 3s are 9. 9 3s are 27 plus 6 is 33. So that means the range of the composite function g f of x is from 6, which is less than or equal to g f of x, up to 33. Part 3, the last part of the functions question, determine the inverse of this composite function g f of x. So finding inverse, let's write the formula g f of x is equal to x cubed plus 6. And what we really want to do is make x the subject of the formula and then switch them. G f of x minus 6 is equal to x cubed. We're subtracting 6 on the right hand side and 6 on the left hand side. And we want to find x. So that will be the cube root of g f of x minus 6. And now that we put it into this form where x is the subject of the formula, we can now substitute g f of x, the composite function, to now be x. And x on the right hand side to be the inverse. So we're going to get the cube root of x minus 6 is the inverse of the composite function. So what that really means is that if we're going from the domain to the range using the composite function, that will be x cubed plus 6. And if we're at the range and we're going backwards, that will be g inverse. Then that will be the cube root of x minus 6. Part B. If x plus 2 is a factor of f of x, which is equal to 2x cubed minus 3x squared minus 4x plus a, find the value of a. So that means that this is part of the subtopic algebra. And we're looking at the factor theorem. So let f of x equal to 2x cubed minus 3x squared minus 4x plus a, for x plus 2 being a factor, which means that we can make x is subject to the formula x plus 2 is equal to 0, so x is equal to minus 2. So we're going to substitute x as minus 2 into that function. So f of minus 2 is equal to 2 by minus 2 cubed minus 3 by minus 2 squared minus 4 by minus 2 plus a. And since x plus 2 is a factor, it means that when we substitute this, it will give us 0. So 0 is equal to minus 2 cubed is minus 2 times minus 2 times minus 2, which is minus 8 by 2 is minus 16. And then minus 2 squared is minus 2 by minus 2 is 4. 4 by minus 3 is minus 12. Minus 4 by minus 2 is plus 8 plus a. And if we notice on this line here, we're only missing one unknown. So we can solve. So 0 is equal to minus 16 minus 12 is minus 28 plus 8 is minus 20 plus a. So a is equal to 20. And we found the value of a in order that x plus 2 is a factor of that function. So that tells us that the only time x plus 2 is a factor of this function, f of x, is when a is equal to 20. May 2012, number 1C. Solve the equation 3 to the power 2x minus 9 times 3 to the power minus 2x is equal to 8. So this tells us that this is in part B of the section quadratics, and specifically we are looking at reducible form of equation. So let's write back the equation 3 to the 2x, and let's bring the 8 across, so everything will be equal to 0. So we get 3 to the 2x minus 8 minus 9 times 3 to the minus 2x. And there are a couple of ways to do this. So one way is let's multiply throughout by 3 to the power 2x. So each term on the left and right hand side of the equation is multiplied by that. And let's substitute y is equal to 3 to the power 2x. So we're going to get y by y, or y squared, minus 8 times y minus 9, because 3 to the power 2x times 3 to the power minus 2x will give us 1. They'll cancel off each other. Is equal to on the right hand side, 0 times anything is 0. So we've converted that difficult equation into something which is a simple quadratic. And we can solve that. Let's use the quadratic formula. A is equal to 1, b is equal to minus 8, and c is equal to minus 9. And we're substituting into the quadratic formula minus b plus or minus the square root of the discriminant all over 2a. So that will give us y is equal to minus, what's b? Minus 8 plus or minus the square root of b squared, which is minus 8 squared, minus 4 times a, which is 1, times c, which is minus 9, all over 2 times a, 2 times 1. So y is equal to minus minus 8, that's 8, plus or minus, minus 8 squared is 64, minus 4 times 1 times minus 9 is plus 36, 64 plus 36 is 100. So 8 plus or minus the square root of 100 all over 2 ones are 2. So either y is equal to 8 plus the square root of 100 is 10 over 2, or y is equal to 8 minus 10 over 2. And 8 plus 10 is 18, 20, 18, 9. So we know y, or 3 to the power 2x is equal to 9, or 3 to the power 2x is equal to minus 1. Well, let's recall that 3 to any power must be something that is positive. So 3 to the 2x equal to minus 1 is not a possible answer. So we're left with 3 to the power 2 to the x is equal to 9. And there are a couple of ways to solve this. We can say 3 to the power 2x is equal to 3 to the power 2, or 3 squared, because 3 squared is equal to 9. As such, 2x is equal to 2, so x is equal to 1. So when x is equal to 1, if we substitute back into the original equation, given up on top, then we can say 3 to the power 2 times 1 is 2. So 3 to the power 2, which is 3 squared, or 9, minus 9 times 3 to the power minus 2 times 1 is minus 2. which that will give us 1/9. So 9 times 1/9 is 1, so 9 take away 1 is 8, and it works. For part D, express x cubed is equal to 10 to the power x to the minus 3 in the form log x to the base 10 is equal to ax plus b. So this is on the subtopic D, Surds, Indices and Logarithms. And what we're doing here is looking to convert from indices to logarithms and manipulate it until it looks like a linear form. And why is it we generally want to make it into a linear form? Because these sorts of equations actually happen in the real world and it's difficult to solve as an indice. But if we convert it into a linear form, we can plot a graph, we can find the gradient, we can find the y-intercept. So let's go for it. X cubed is equal to 10 to the power x minus 3. So if we log both sides, we're going to get log x cubed to base 10 is equal to log 10 to the power x minus 3 to base 10. So we can use the formula log x to the n, it will be n log x, meaning that any power we have of x there, when we're logging it, we can bring it in front. So that would means we can rewrite 3 log x to base 10 is equal to x minus 3 times log 10 to base 10. And we can simplify that because on the right hand side, log 10 to base 10 is 1. So we have 3 log x to base 10 is equal to x minus 3. So we can have log x to base 10 is equal to x minus 3 over 3. We almost have it in the form we want. So we can separate it. And we get log x to base 10 is equal to x over 3 or 1/3 x minus 3 over 3, which is 1. So a is equal to 1/3 and b is equal to minus 1. In D part 2, hence state the value of the gradient of a graph of log x to base 10 versus x. So if we consider log x to base 10, and what they're telling us here is imagine plotting a straight line graph y is equal to ax plus b, where y is equal to log x to base 10, and we're plotting it versus x. What is the gradient? The gradient will be a, which we worked out in part 1 to be 1/3. May 2012, number 2a. The quadratic equation x squared minus 4x plus 6 is equal to 0, where alpha and beta are the roots. Calculate the values of alpha squared plus beta squared. So let's write the equation x squared minus 4x plus 6 is equal to 0. And the coefficients are a is equal to 1, a being the coefficient of x squared, b is equal to minus 4, and c is equal to 6. So when we're finding the sum of the roots, that will be equal to minus b over a, which is minus of, what is b? Minus 4 all over 1. Minus 4 is 4, 1 into 4 is 4. So that's the sum of the roots, meaning alpha plus beta is equal to 4. And the product of roots, which is alpha beta, is equal to c over a. And c is 6 over 1, 1 into 6 is 6. And since we want to find alpha squared plus beta squared, let's expand alpha plus beta squared. So alpha plus beta squared is alpha squared plus 2 alpha beta plus beta squared. Alpha squared plus beta squared on the left hand side, we can carry across the 2 alpha beta, it's adding on the left hand side, when we carry across it will subtract, so that will give us alpha plus beta all squared minus 2 alpha beta. Alpha plus beta is the sum of the roots, which is 4, and alpha beta is the product of the roots, which is 6. So we can substitute. So alpha squared plus beta squared is equal to 4 squared minus 2 times 6. 4 4 is 16 minus 12. So alpha squared plus beta squared, which is what we want to find, works out to be 4. And for part B of the question, find the range of values of x for which 2x minus 5 all over 3x plus 1 is greater than 0. So this is actually in part C of the subtopics, which is inequalities. And this specifically looks at solving rational linear inequalities. So in order to solve this, let's multiply throughout by whatever the denominator is squared. So we'll multiply on the left side and the right side of the inequality by the same thing. So we get 2x minus 5 all over 3x plus 1 multiplied by 3x plus 1 squared. Whatever the denominator is squared. That's a little method or a little trick to help us. And we'll do the same thing on the right hand side. So 0 times 3x plus 1 all squared. On the left hand side, the denominator 3x plus 1 will cancel with one of those. So we're left with 2x minus 5 times 3x plus 1 is greater than 0, because 0 times anything on the right hand side is 0. So we now have a linear times a linear, which means we have a quadratic on the left hand side is greater than 0. So let's consider that this was a graph, and let's look for the roots. So if we consider 2x minus 5 times 3x plus 1 is equal to 0, and we're putting it to be equal to 0 so we can find the roots. Either 2x minus 5 is equal to 0, which means 2x is equal to 5, so x is equal to 5 over 2, so that will be a root of the equation. Or 3x plus 1 is equal to 0, so 3x is equal to minus 1, which means x is equal to minus 1/3. Let's make a sketch to help visualize what's happening. Since we have that equation 2x minus 5 times 3x plus 1, if we multiply it, we get 2x times 3x is 6x squared. Why is that important? It means that a is equal to 6, so a is positive, so this is a U-shaped graph. And we know the two roots. One is positive at 5/2, and one is negative at minus 1/3. So if we sketch that, what does it tell us? And we want to find this quadratic which is greater than 0, meaning where are the y values greater than 0? Well, if we look at the root on the right hand side, 5/2, then is everything to the right of it, then y is positive, and everything to the left of minus 1/3. So x must be greater than 5/2, and x must be less than minus 1/3. And we could write it together as such. Thus, minus 1/3 is greater than x, which is greater than 5/2. For those range of values, you will find that this solves the rational inequality given in the question up on top. And let's just substitute 1 so you can see it. So if x is greater than 5/2, we can imagine x to be 3. Look at the first line. If we put x as 3 in there, 2 3s are 6, take away 5, that's 1 on top. And 3 3s are 9, plus 1 is 10. So 1 over 10. 1 over 10, or 1/10, is greater than 0. So it works. And if x is less than minus 1/3, we can pick minus 1 and do the same thing, and you'll see it works as well. So always remember that when we get these solutions and we're given a range or an inequality, we can substitute in there to show that it's working, to double check our answer. May 2012, number 2C. A customer repays a loan by increasing the payment each month by X dollars. If the customer repaid $50 in the first month and $70 in the 9th month, calculate the total amount of money repaid at the end of the 24th month. So we can see that this is in topic E, sequences and series, and this is looking at an AP. And that's because there's a constant increase each month, meaning there's a common difference. So the common difference, D, is equal to X. T to the fifth term is equal to 50. The 9th term, or the 9th month, is equal to 70. And the general formula for an AP, because we're dealing with common difference, T to the n is equal to A plus n minus 1 T. And if we substitute, for the 5th term, T to the 5 is equal to A plus 5 minus 1 X. Because we know n is 5 in this case, and we know the common difference is X. And that gives us 50 is equal to A plus 4X. And similarly, T to the 9th is equal to A plus 9 minus 1 X, because n is 9. And if we substitute, that will mean 70 is equal to A plus 8X. Now we have two simultaneous equations, and we can solve. 50 is equal to A plus 4X, and 70 is equal to A plus 8X. And if we subtract, we're going to get minus 20 is equal to minus 4X. As such, X is equal to minus 20 divided by minus 4. So X is equal to 5. That means that each month the common difference is 5. So it's increasing from 50 to 55, 55 to 60, 65 to 70. And if we substitute that X is equal to 5 into any one of the equations, so let's take 50, the first equation, 50 is equal to A plus 4X. Then we're going to get 50 is equal to A plus 4 times 5. 4 5s are 20. And if we carry it across, 50 minus 20. So that means that 30 is equal to our first term, A. So the question asks us to calculate the total amount of money we paid at the end of the 24th month. So s to the n is equal to n on 2 by 2a plus n minus 1d. And s to the 24 is equal to 24 over 2 times 2 by what is a, 30, plus 24 minus 1 by what is d, 5. And you have your calculators, that will give us $2,100. So the total amount of money we paid at the end of the 24th month, or the end of 2 years, is $2,100. May 2013, number 1a. Let f of x equal to x cubed minus x squared minus 14x plus 24. Part 1. Use the factor theorem to show that x plus 4 is a factor of f of x. So what they're asking us to do is to show a proof. So we know f of x, so let's write that f of x is equal to x cubed minus x squared minus 14x plus 24. And if we're going to use x plus 4, so we can assume x plus 4 is equal to 0, so x is equal to minus 4, and that's what we're going to substitute in the factor theorem. So f of minus 4 is equal to minus 4 cubed minus, and what's x squared? Minus 4 squared, minus 14x will be minus 14 times minus 4 plus 24. And that works out to be minus 64 minus 16, because minus 4 squared is 16, minus 14 times minus 4 is plus 56 plus 24, and that works out to be 0. And since the remainder works out to be 0, it means that x plus 4 is a factor. And we have shown the proof, so we can draw that small rectangle or write QED to show that we have completed the proof. Part 2. Determine the other linear factors. So we have a polynomial of degree 3, meaning the highest power of x in it is x to the power 3. And let's write that f of x equal to x cubed minus x squared minus 14x plus 24, which is equal to x plus 4, because that's a factor, times some quadratic. And we'll call that ax squared plus bx plus c. So, by the principle of undetermined coefficients, we're going to compare the coefficients of x cubed. So how do we get x cubed? On the left-hand side, we know it's 1x cubed. On the right-hand side, how do you get x cubed? We take the x plus 4, and we multiply it by ax squared. And that's the only way we can get an x cubed term. So if we compare those coefficients, then we're going to get 1 is equal to a. And now do the same thing for x squared terms. On the left-hand side, we know it's minus 1x squared. And on the right-hand side, how do we get x squared terms? We take the second term in the first linear factor, that's 4, and we multiply it by 1x squared, because a is 1. And we take the x term, the first term in the first factor, and multiply it by bx. If we remove the x squared throughout, we're going to get left with minus 1 on the left-hand side is equal to 4 ones are 4 plus b. As such, if we take the 4 and carry it across, it'll become minus 4, so you get minus 1 minus 4, minus 5 is equal to b. So we found a and we found b. And now let's compare the coefficients of x to the power 0, or we could say the term without an x, on both sides. So on the left-hand side, it's 24, and on the right-hand side, it'll be 4 times c. So c will be 24 divided by 4. As such, c is equal to 6. So we have f of x equal to x plus 4 by x squared, because a was 1, minus 5x, because b was minus 5, plus 6, because c is 6. And we could factorize that quadratic, so our final answer will be x plus 4 by x minus 2 by x minus 3. And that gives our 3 linear factors of this particular f of x polynomial. May 2013, number 1b. A function f of x is given by f of x is equal to 2x minus 1 divided by x plus 2. Part 1. Find an expression for the inverse function f inverse x. So this topic is functions, which was on the old syllabus and no longer on the new one, but we'll go through the solution just for you to build some concept. F of x is equal to 2x minus 1 over x plus 2, and if we want to find f inverse, what we need to do is make x the subject of the formula. And there are a couple different ways to do it. This is the method that I'm choosing, because I've found it easier for my students. So we take the denominator on the right hand side and carry it across. So it becomes the numerator on the left-hand side. So we'll get x plus 2 by f of x is equal to 2x minus 1. And we can expand the left-hand side. We will get x by f of x plus 2f of x is equal to 2x minus 1. And we can put all the x's on one side, on the left-hand side, and everything else on the right-hand side. So we'll bring across the 2x, so it will be x f of x minus 2x is equal to, take the 2f of x on the left side and carry it across to the right. So we'll get minus 2f of x because it was adding, and now it's doing the opposite, minus 1. So we can factorize out the x on the left-hand side. So we get x by f of x minus 2 is equal to minus 2f of x minus 1. So if we want to find x alone, so what we're doing is finding the subject of the formula or transposing to find x. So x is equal to minus 2f of x minus 1 all over f of x minus 2. And if you want to write it in the form of the inverse, so replace x by f inverse x on the left-hand side, and on the right-hand side, we replace f of x by x. So that will give us f inverse x is equal to minus 2x minus 1 all over x minus 2. Part 2. The function g is given by g of x is equal to x plus 1. Write an expression for the composite function fg of x and simplify your answer. So if we look at the composite function fg of x, the first function which is working on x is the function g. So we can write g of x is equal to x plus 1, we know that. So what that means, we're going to rewrite fg of x, and we're replacing g of x, let's put the blue arrow so you can see, by what is g of x? We just worked that out, x plus 1. So fg of x becomes f of x plus 1. So we know the function for x, f of x is equal to 2x minus 1 over x plus 2. And we want to replace x by x plus 1. So wherever we have x on the right-hand side, let's replace it by x plus 1. So that will be 2 by x plus 1 minus 1 over x plus 1 plus 2. And we can expand the brackets and simplify. So that will give us 2x plus 2 minus 1 all over x plus 1 plus 2. And that works out to be 2x plus 1 over x plus 3. As such, the composite function fg of x is equal to 2x plus 1 all over x plus 3. Part C. Given that 5 to the power 3x minus 2 is equal to 7 to the power x plus 2, show that x is equal to 2 log 5 plus log 7 all over log 125 minus log 7. So we can see this falls under the topic of Surds, indices, and logarithms. And we have our question as indices up on top. So let's write that. 5 to the power 3x minus 2 is equal to 7 to the power x plus 2. So there's a proof that is required that x is equal to something in terms of logs. So we're changing from indices to logarithms. So if we log both sides, and by the rule that log x to the n will be equal to n log x, meaning the power that we're logging can be brought in front. So that's going to give us 3x minus 2 in brackets log 5 to base 10 is equal to x plus 2 log 7 to base 10. And the base 10 is understood, so we don't write it. So now what we want to do is expand the brackets and transpose, so we could get x as the subject of the formula. So 3x log 5 minus 2 log 5 is equal to x log 7 plus 2 log 7. And we could bring all the x's on one side as we proceed to transpose. So 3x log 5 minus x log 7 is equal to minus 2 log 5, when we carry it across, will be 2 log 5 plus 2 log 7. And we can factorize. So this is looking similar to what we did in part 1. We're factorizing out the x, so we're left with 3 log 5 minus log 7 is equal to 2 log 5 plus log 7. And this right-hand side starts to look like our numerator that we want to prove. The denominator looks slightly different. So let's see if we can adjust. We already have the log 7, but we need to get log 125. That 3 log 5 can be converted to log 5 to the power or to the index 3. So x log 5 cubed minus log 7 is equal to 2 log 5 plus log 7. And we work out a 5 to the power 3. So that will be x, and in brackets log 125. 5 5s are 25. 25 by 5 is 125. Minus log 7 is equal to 2 log 5 plus log 7. So x is equal to 2 log 5 plus log 7, and let's carry that across. It will be in the denominator, log 125 minus log 7. And we have shown the proof. So we can draw our little rectangle there, or write QED to represent such. May 2013, number 2a. Let f of x equal to 3x squared plus 6x minus 1. Part 1. Express f of x in the form a x plus h squared plus k, where h and k are constants. So we can see that we have an algebra question here, and we're converting it into the form so it looks like completing the square. So let's rewrite the equation. F of x equal to 3x squared plus 6x minus 1. And the first thing we want to do is extract the coefficient of x squared outside. That will give us f of x is equal to 3, and in curly brackets, x squared plus 2x minus 1. And that shows immediately that a is equal to 3. Now, there are quite a few ways to move it from the original form into the form of completing the square. I found that my students have the best grasp when we use algebra tiles. So we're going to do that here. Notice that we have 3 times x squared plus 2x in curly brackets. So let's bring that up. We have 3 times, and let's put a little oval here, x squared. So that's in yellow, which is really a length of x times x times 1 in brown, and x by 1, those are the dimensions, minus 1. And if we recall from the use of algebra tiles, when we have a negative, we normally use that as red. So that's a 1 by 1 square. So if we consider 3 times anything, which is like repeated addition, it means we have 3 sets of what is in the blue oval there. And then we minus 1. So let's separate it out. So we'll pull out our x squared, and we'll slide one of the x's down, and we'll rotate and slide the other one down. And what's the reason for doing that? We're trying to form a square. So if we look at the top of it, we know the length of the yellow. So if we put dimensions onto this here, we'll see that the width of the yellow square is x, and of the brown square is plus 1. And if we go on the left hand side, we'll see that dimension is x. So x by x is x squared. That gives us the yellow square. And 1 times x is 1x. And so that gives us the brown rectangle. And similarly, we have plus 1 at the base, which means 1 times x is 1x. So everything makes sense. And if we look at this square here, this square looks perfect. X plus 1 by x plus 1. So x plus 1 squared. Except we're missing a space. So how do we fill that space? Now, one of the things to remember in algebra tiles, we can add a green square and a red square because, and let's remind each other that the fact is that you can pick any colors for the x squared, for the x, and for the numbers. It's just that when we're doing the negative of it, which is the flip of that tile, they will be red. So if we have a green square and a red square, that indicates plus 1 minus 1. And plus 1 minus 1 is equal to 0. So if we add these two squares, which total is 0 to anything, then the value doesn't change. So let's slide that green square down and then the red square. So we're adding 0 to what we have. So the value doesn't change. We have x plus 1 squared, which is the yellow, the 2 browns, and the green, minus 1, which is the red. And there are 3 sets of that. So let's slide it across. So that gives us a second set, and let's slide the next one, so that gives us the third set. So this here is an indication of 3 sets of x squared plus 2x, plus 1 minus 1. And from the original equation up on top, what was missing? Minus 1. So we can bring that across. So what do we have in all? Let's write that. F of x is equal to 3 times x plus 1 squared minus 1. 3 sets of that. minus 1 on the right hand side, that one red square. And now we can just expand the brackets. So 3 times x plus 1 squared, and 3 times minus 1 is minus 3 minus 1. So that will give us 3 times x plus 1 squared minus 4. So we've completed the square in 5 lines of working, and the first line was the actual equation. Part 2, state the minimum value of f of x. And if we have it in this form, the smallest value of anything that's being squared is 0. So if we consider that the squared part works out to be 0, then f of x is equal to minus 4. That will be the minimum value. And part 3, determine the value of x for which f of x is a minimum. In order for the minimum to occur, it meant that the brackets worked out to be 0. So x plus 1 is equal to 0. So x is equal to minus 1. May 2013, number 2b. Find the set of values of x for which 2x squared plus 3x minus 5 is greater than or equal to 0. So we can see that this is within the topic of inequalities. So let's consider 2x squared plus 3x minus 5 is equal to 0. And if we factorize it, we're going to get 2x plus 5 by x minus 1 is equal to 0. And the reason that we're doing this is that we can actually identify where the roots are. So either 2x plus 5 is equal to 0, which means 2x is equal to minus 5, and x will be equal to minus 5 divided by 2, or minus 2.5, or x minus 1 is equal to 0, which means that x is equal to 1. So if we bring up a little graph and we identify where the roots are, and if we look at the original polynomial, we can see that the coefficient of x squared is positive, which means it's a U-shaped graph. From this, the equation is asking us where is y greater than or equal to 0. So if we look at the root on the right-hand side, where x is equal to 1, for y to be greater than or equal to 0, it means x must be greater than or equal to 1. And similarly, at the root where x is equal to minus 5 over 2 or minus 2.5, in order for y to be positive, x must be less than or equal to minus 5 on 2. Thus, if we put it together, we will get minus 5 on 2 is greater than or equal to x, which is greater than or equal to 1. Part C. Find the sum to infinity of the following series: 1 over 4 plus 2 over 4 squared plus 1 over 4 cubed plus 2 over 4 to the 4th, and continuing. So we can tell that this falls within series and sequences. Take a note, this series can be written as the sum of two geometric series. So let's do that. We want to find the sum to infinity of this series. So let s to infinity be equal to the series 1 over 4 plus 2 over 4 squared, continuing. And if we rearrange it, we can say the sum to infinity be 1 over 4 plus 1 over 4 cubed plus 1 over 4 to the 5th and so forth, plus 2 over 4 squared plus 2 over 4 to the 4th plus 2 over 4 to the 6th. So we can say sum to infinity will be sum to the first series plus sum to the second series. So sum to the first series, the infinity of that is a over 1 minus r. And if we substitute, if we look at the first series, we know a, the first term is 1 over 4. And how do we go from the first term to the second term and so forth? We're multiplying by 1 over 4 squared. So that will be r, the common ratio. So if we substitute, we're going to get 1 over 4 or a quarter divided by 1 minus 1 over 4 squared. And of course the denominator works out to be 15/16. You can use a calculator so you can work it out. So if we're dividing fractions, it'll be 1 over 4 multiplied by 16 over 15, the reciprocal, which works out to be 4 over 15. So the sum to infinity of the first series is 4/15. And if we do the same for the second series, let's look at it again. What is the value of a? A will be 2 over 4 squared. And how do we go from the first term to the second term and so forth? So we're multiplying by 1 over 4 to the squared, which means that's the common ratio. So as we substitute into the second series, we're going to get 2 over 4 squared, which is a over 1 minus 1 over 4 to the squared. And 4 squared is 16, so it will be 2 over 16 multiplied by 16 over 15, which works out to be 2 over 15 is the sum to infinity of the second series. So the sum to infinity in total would be 4 over 15 plus 2 over 15. So the sum to infinity of the following series is 6 over 15. May 2014, number 1a, part 1. The function f is defined as f of x equal to 1 minus x squared, where x is a real number. Show that f is not 1 to 1. So f of x is equal to 1 minus x squared. And let's substitute when x is equal to 1. F of 1 works out to be 1 minus 1 squared, which is 0. And let's substitute when x is equal to minus 1. F of x is equal to 1 minus 1 squared, which is also 0. So if we look at our diagram down below, where we have on the domain in the dark gray, when x is 1, it goes to the range value of 0. And when x is minus 1, it also goes to 0. So f is not a 1-to-1 mapping. Part 2, the function g is defined by g of x is equal to a half x minus 3, where x are real numbers. Find fg of x and clearly state its domain. So fg of x, and we know that with respect to x, the first function that's acting on it is g. So we can write that g of x is equal to a half x minus 3. So we can bring up our blue arrow to show that we already found what g of x is. So we can substitute there. So we get f a half x minus 3. And let's write our formula, f of x equal to 1 minus x squared from part 1. And we can substitute f of a half x minus 3. So wherever we have x, we're replacing it by this new linear expression, a half x minus 3. So that means on the right hand side will be equal to 1 minus a half x minus 3 all squared. I could expand that. So that will give us 1 minus a quarter x squared minus 3x plus 9. And we can remove the bracket. So we're going to get 1 minus a quarter x squared plus 3x minus 9. So the composite function fg of x is equal to minus a quarter x squared plus 3x minus 8. Part B, determine the g inverse of the function g and sketch on the same pair of axes graphs of g and g inverse. G of x is equal to a half x minus 3. And what we're going to do is make x the subject of the formula. Gx plus 3 is equal to a half x. X will be equal to 2 times g of x plus 3. And if we substitute accordingly, then we replace g of x by x and replace x by g inverse x. So 2 of x plus 3 is equal to g inverse x. So we found the inverse. G inverse is equal to 2x plus 6. If we look at our sketch, we can see our red line, which indicates g of x, which is a half x minus 3. And if we include now g inverse x, which is 2x plus 6, they're intercepting at minus 6, minus 6. And how can we describe the red line to the green line, the g of x to the g inverse x? It is about a reflection about the line y is equal to x, which we have in purple. May 2014, number 1b, when the expression 2x cubed plus ax squared minus 5x minus 2 is divided by 2x minus 1, the remainder is 3.5. Determine the values of the constant a. This is within the subtopic of remainder theorem, which falls under algebra in section 1 of our syllabus. Let f of x equal to 2x cubed plus ax squared minus 5x minus 2. And if we have 2x minus 1, let's put that equal to 0. So 2x equal to 1, as such x is equal to a half. So we're going to substitute that. F of a half would be equal to 2 by a half cubed plus a by a half squared minus 5 by a half minus 2. It's just a direct substitution of x to be in a half. And we know that the remainder is minus 3.5. So minus 3.5 will be equal to a half cube is 1/8. 2 times 1/8 is a quarter. Plus a half squared is a quarter plus a quarter a minus 5 on 2 minus 2. So we can simplify. We can carry the Numbers of course on the left hand side and leave the a on this side to solve. So we're going to get a 3/4 is equal to 1/4 a. So a is equal to 3. So when a is equal to 3 and it's been divided by 2x minus 1, the remainder will be 3.5. Part C. The length of a rectangular kitchen is y meters and the width is x meters. So let's bring up a blue rectangle to indicate such. And it's always a good thing to draw a little sketch of what's happening so we can get a better grasp. If the length of the kitchen is half the square of its width and its perimeter is 48 meters, find the values of x and y, which are the dimensions of the kitchen. So for the first part, if the length of the kitchen is half the square of its width, that means that y is equal to half x squared. And its perimeter is equal to 48, so perimeter will be y plus x plus y plus x. We're just going around, start from one point and let's move. And we know the perimeter is 48, so 48 is equal to 2y plus 2x. At this point in time, we have two equations, so we can substitute for y into there. So we're going to get 48 is equal to 2 by a half x squared plus 2x. So solving for a quadratic equation, remember we make one side equal to 0. So 0 is equal to x squared. 2 times a half is 1, so 1x squared plus 2x minus 48. At this point in time, there are multiple ways to solve this. We can use the quadratic formula or we can factorize. So let's factorize. 0 is equal to x plus 8 by x minus 6. Either the first bracket is 0, x plus 8 is equal to 0, so x is equal to minus 8. Or the second bracket is equal to 0. X minus 6 is equal to 0, so x is equal to 6. And if we have two solutions, x in this case must be positive because we can't get a negative length. As such, x is equal to 6. And if we know x is equal to 6, we can solve for y. In either of the equations, we can substitute. So y is equal to half x squared. So y is equal to half by 6 squared. 6 squared is 36. Half of 36 is 18 meters. So x is equal to 6 meters and y is equal to 18 meters. May 2014, number 2a. Given that f of x is equal to minus 2x squared minus 12x minus 9. Part 1. Express f of x in the form k plus a by x plus h squared, where h and k are integers to be determined. So this is another completing the square question, just as what came in the previous year, May 2013, number 2a. In that method, we used algebra tiles to solve. In this case, we'll use a different method. So let's rewrite the formula. F of x is equal to minus 2x squared minus 12x minus 9. And the first thing to do is factorize out the coefficient of x squared, which is minus 2. So that will give us minus 2 by x squared plus 6x. And we could leave the minus 9 by itself. So what we're really doing, let's rewrite that first part. I'll put some curly brackets around it to emphasize this is the area that we're dealing with that we have to convert into a perfect square. And we'll have the minus 9 outside. So minus 2 x squared plus 6x. And what we want to do is take the 6x and split it into 2. So that will be 3. And then we're squaring it. So we want to add 9 minus 9. The reason for doing such, 9 minus 9 is 0. So we're not actually creating a new formula, we're just changing the form. So if we take the first three terms, so minus 2, x squared plus 6x plus 9, and we move the minus 9 outside, so the minus 9 by minus 2 is plus 18 minus 9. Then we're about to solve. So we have minus 2, and x squared plus 6x plus 9 is really x plus 3 squared, plus 18 minus 9 is plus 9. And if you're getting problems with that, then you could go factorize x squared plus 6x plus 9 and you'll end up with x plus 3 by x plus 3. Part 2. State the maximum value of f of x. So f of x is, let's write it in that form that we just got, minus 2 x plus 3 squared plus 9. And how do we get the maximum value? It will be when the brackets works out to be 0. And when the brackets works out to be 0, then f of x will be equal to 9. Part 3. Determine the value of x for which f of x is a maximum. So how did that happen? It is when the brackets x plus 3 is equal to 0. So x will be equal to minus 3. And let me show you what the graph looks like. So when we bring up the graph, we can see it intersecting at 2 points there. But more importantly, for completing the square, we can find the maximum point, which is minus 3, 9. Part B. Find the set of values of x for which 3 plus 5x minus 2x squared is less than or equal to 0. When we're dealing with these inequalities, we can consider that it's equal to 0, so we can find the roots. And if we factorize that, we're going to get 3 minus x by 1 plus 2x. Let's recall that in this YouTube channel where we're dealing with Add Maths, we assume that we know how to factorize properly. And if we're getting problems, you could go back to my math channel where I went through many questions showing how to do factorization of quadratic. We have the multiplication of two brackets equal to 0. So either the first bracket, 3 minus x is equal to 0, which means that 3 is equal to x, or the second bracket is equal to 0, 1 plus 2x is equal to 0. So 2x is equal to minus 1, so x is equal to minus a half. And if we look at the sketch, remember the coefficient is negative again. So if we make that sketch and we put in the roots at x equal to 3 and x is equal to minus a half or minus 0.5, then when is this curve, which we have in red, less than or equal to 0? It is when it's below the x-axis. So if we take the root on the right-hand side where x is equal to 3, for the y value to be negative, then it means it's counting from 3 and moving to the right. So we shade that in blue. And so x must be greater than or equal to 3. Similarly, if we take the other root, which is minus a half or minus 0.5, and we were looking at where the y value becomes negative, it's going to the left of it. So in that case, x must be less than or equal to minus a half. And if we put them together, we can write it as one line as minus a half is greater than or equal to x, which is greater than or equal to 3. May 2014, number 2C. A series is given by 0.2 plus 0.02 plus 0.002 and so forth. Part 1. Show that this series is geometric. If a series is geometric, then if we divide two consecutive terms, we should be getting the same constant value or constant ratio. So let's divide t on 2 divided by t on 1. That will be equal to 0.02 divided by 0.2, which is equal to 0.1. And if we try t on 3 divided by t on 2, it will give us the same value. And t on 4 divided by t on 3 gives you the same value, which is r. So r is 0.1, so it's proven as a geometric series. So we can draw a little square or write QED because we've shown the proof. Part 2. Find the sum to infinity of this series, giving your answer as an exact fraction. So let's recall the formula that's given in the formula sheet. S of infinity is equal to a 1 minus r. And we can substitute. We know a, the first term, is 0.2 all over 1 minus, what's r? 0.1. So 0.2 over 0.9 works out to be 2 nines. May 2015, number 1a. The functions f and g are defined by f of x is equal to x squared plus 5 for x greater than or equal to 1, and g of x is equal to 4x minus 3 for x being a real number. Find the value of g f of 2. So for this composite function, let's write it down, g f of 2. First thing we want to do is look at the element 2 and what function is acting on it. First of all, it will be f. We'll write the function f of x equal to x squared plus 5 as given above, and we'll substitute x as 2. Wherever we have x, we will replace it by 2. So that will give us f of 2 is equal to 2 squared plus 5. So f of 2 is equal to 9. And if we look on the right side in the dark gray, let's consider that to be our domain, where x was 2, and under the function f, it became 9. So that was the range. Now, instead of writing g f of 2, we just worked out f of 2. That was 9, so let's replace it. Let's bring up the blue arrow to show that we're replacing f of 2 by 9. So we have g of 9. So let's write the function g of x is equal to 4x minus 3, and substitute x as 9. So g of 9 is equal to 4 times 9 minus 3. 4 9 is 36, so 36 take away 3 is 33. So that's now like saying that the green oval we have on the right hand side is now our domain, where the element in it is 9, and the function g is acting on it. Part B. The function h is defined by h of x is equal to 3x plus 5 all over x minus 2, where x are real numbers and x is not equal to 2. And the reason x is not equal to 2, if we substitute x is equal to 2 in that function h of x, the denominator works out to be 0, and anything over 0 is an error. Determine the inverse of h of x. So if you have h of x equal to 3x plus 5 over x minus 2, let's put brackets around them. And in order to find the inverse, what we want to do is be able to make x the subject of the formula. So let's take the x minus 2, which is the denominator on the right hand side, and carry it across. So it will give us x minus 2 by h of x is equal to 3x plus 5. And we now expand x h of x minus 2h of x is equal to 3x plus 5. And we want to put all the x's on one side. So x h of x minus 3x, because the 3x was adding on the right hand side, and when we bring it across the equal sign, we'll do the additive inverse, which is subtract. And that is equal to plus 2h of x plus 5. So we can now factorize out the x on the left hand side. So that will give us x h of x minus 3 is equal to 2h of x plus 5. And now we can transpose completely and say x is equal to 2h of x plus 5 all over h of x minus 3. Now we want h inverse. So let's replace x on the left hand side by h inverse x. And on the right hand side where we had h of x, wherever that is, we replace it by x. So h inverse x is equal to 2x plus 5 over x minus 3. And that's the inverse of the function. May 2015, number 1c. Given that x minus 2 is a factor of k of x, which is equal to 2x cubed minus 5x squared plus x plus 2, factorize k of x completely. So we're trying to find the linear factors of this polynomial to the degree 3, and we know x minus 2 is a factor. So we can rewrite it. 2x cubed minus 5x squared plus x plus 2 is equal to x minus 2, which is a factor, multiplied by a quadratic. Because a linear times a quadratic will give us a cubic. Let's compare the coefficients of x cubed. On the left hand side, that is 2. And on the right hand side, how do we get x cubed? We multiply the first term in the linear by the first term in the quadratic. Because that will be 1x times ax squared. So that's 1 times a, because we know we're just comparing the coefficients, the numbers in front of the x cubed. So 2 is equal to a. Let's do the same for x squared. On the left hand side, it's minus 5. On the right hand side, how do we get x squared? We take the first term in the linear and multiply it by the middle term. So x times bx. So if we're just looking at the coefficients, it will be 1 times b. And the second term in the linear times the first term in the quadratic. So minus 2 times ax squared. So minus 2 times a. Minus 5 is equal to b minus 2a. And we know a is 2. We worked that out already. So that will be minus 4. So we can solve for b. We take the minus 4 and carry it across. It will be plus 4 minus 5 plus 4 is equal to minus 1. And let's compare the coefficients of x to the power 0. On the left hand side, that is 2. And on the right hand side, it will be the last term of the linear times the last term of the quadratic. So it will be minus 2 times c. So if we want c, it will be 2 divided by minus 2, which is minus 1. So we found a, b, and c. So we can now rewrite it. That is equal to x minus 2 by 2x squared, because a was 2, minus x, because b is minus 1, minus 1, that's c. And we can factorize that quadratic. So we will get x minus 2 by 2x plus 1 by x minus 1. So k to the x is equal to the product of these three linear factors. Part D, solve the following equations. Part 1, 16 to the power x plus 2 is equal to a quarter. So we can rewrite it as 4 squared to the power x plus 2 is equal to 4 to the power minus 1. And using the rules of indices, then we can multiply the powers up and top. So it will be 2 times 4 to the power 2 times x plus 2 is equal to 4 to the power minus 1. If we compare the indices, we will have 2 times x plus 2 is equal to minus 1. And let's expand and solve. That will give us 2x plus 4 is equal to minus 1. So 2x is equal to minus 1 minus 4, which is minus 5. So x is equal to minus 5 over 2. This tells us that when x is equal to minus 5 on 2, the left-hand side will be equal to a quarter. And if you want, we can substitute it in there. We can see 16 to the power minus 5 on 2 plus 2. Minus 5 on 2 plus 2 works out to be minus a half. So 16 to the power minus a half would be 1 over 16 to the power half, which means 1 over the square root of 16, which is a quarter, so it works out. And you can use a calculator to double check as well. Part 2, solve the following equation. Log x plus 2 to base 3 plus log x minus 1 to base 3 equal log 6x minus 8 to base 3. So if we apply the rules of logarithms, when we have two of them that are adding, we can multiply them, keeping the base the same. So that will give us log x plus 2 by x minus 1 on the left-hand side to base 3 is equal to log 6 minus 8 to base 3. And since both sides have the same logarithm to base 3, then we can remove those. So we're left with x plus 2 by x minus 1 on the left-hand side is equal to 6x minus 8. We can multiply the linear expressions on the left-hand side, so that will give us x squared plus x minus 2 is equal to 6x minus 8. And if we want to solve for a quadratic, we want to make one side equal to 0. So let's bring everything across from the right-hand side onto the left. So it will be x squared plus x minus 6x minus 2 plus 8 is equal to 0. And we can simplify, so we're going to give us x squared minus 5x plus 6 is equal to 0. And we can factorize that or use the quadratic formula, whichever you prefer. I will factorize, so it will give me x minus 2 by x minus 3 is equal to 0. So either x is equal to 2 or x is equal to 3. And you can check this back by substituting x is equal to 2 into the first line. So you can see the left-hand side works out to be log 4 to base 3, and the right-hand side works out to be log 4 to base 3. So it works. If we substitute 3 into there, we're going to get log 10 on the left-hand side and the same on the right-hand side. So for either x equal to 2 or 3, the solution works. May 2015, number 2a, given that f of x equal to 3x squared minus 9x plus 4, express f of x in the form a, x plus b, all squared plus c, where a, b, and c are real numbers. In May 2013, we solved the completing square question using algebra tiles. In the following year, in 2014, we expanded the brackets. So in 2015, we'll use a different method, so students have a variety to pick from. In this method, there are two simple formulas for the term which is inside the brackets and for the last term. So let's consider that P is equal to 3, Q is equal to minus 9, and R is equal to 4. Normally, when we look at the coefficients of a quadratic, we use A, B, and C as in the quadratic equation. But A, B, and C is the form that we want to change it into. So we need to adjust slightly. So A is equal to P, which is 3. And B, which is the term inside the brackets, is equal to Q over 2P. Just like B on 2A in the quadratic equation formula. And that gives us minus 9 over 2 times 3, which works out to be minus 3 on 2. And C is equal to 4PQR minus Q squared on 4P, or 4AC minus B squared on 4A, if it were the normal terms that we're using. And when we substitute, we're going to get 4 times 3 times 4, which works out to be 48, minus 9 squared, which is 81. 48 minus 81 is minus 33, all over 4 times 3, which is 12. So minus 33 on 12, which is reduced, will give us minus 11 on 4. So the formula f of x is equal to 3, which was a, open brackets, x plus b, which is x minus 3 on 2, all squared, plus c, which is minus 11 on 4. Part 2. State the coordinates for the minimum point of f of x. So x minus 3 is equal to 0. Remember, in order to find the minimum point, what that means is we need to make the brackets as small as possible. And for that to happen, we have to say x minus 3 on 2 is equal to 0. So x is equal to 3 on 2. And when x is equal to 3 on 2, that means f of x is equal to minus 11 on 4. So if we make a little sketch here to show you where the minimum point is, remember we have a U-shaped graph because the coefficient of x squared is 3. It is positive. and it cuts at C, the y-intercept, which is 4. So if you make that sketch there, we can see that the minimum point is at x is equal to 3 on 2, or 1.5, and y is minus 11 on 4, or minus 2.75. Part B. The equation 3x squared minus 6x minus 4 is equal to 0 has roots alpha and beta. Calculate the value of 1 on alpha plus 1 on beta. So 3x squared minus 6x minus 4 is equal to 0. So a is equal to 3, b is equal to minus 6, and c is equal to minus 4. So if you want to find the sum of the roots, which is alpha plus beta, that is equal to minus b over a. And if we substitute, we're going to get minus 6 on 3, which works out to be 3 into 6, 2. The product of the roots alpha beta is equal to c over a, which is minus 4 over 3. 1 on alpha plus 1 on beta, which is what we want to find, is equal to beta plus alpha all over alpha beta. We're just simply adding up fractions using a common denominator. And we can substitute for that because beta plus alpha is the sum of roots, which is 2, over the product of roots alpha beta, which is minus 4 on 3. And we can use our calculators, or we can say 2 times minus 3 on 4. 2 into 2, 1, 2 into 4, 2. So our answer, 1 on alpha plus 1 on beta, is equal to minus 3 on 2. May 2015, number 2C. Determine the points of intersection of the curve 2x squared minus y plus 19 is equal to 0, and the line y plus 11x is equal to 4. So 2x squared minus y plus 19 is equal to 0. Let's call that equation 1. And y plus 11x is equal to 4. So if we add the two equations, then we're going to get 2x squared, and the minus y plus y will cancel, plus 11x plus 19 is equal to 4. And we can bring everything across onto the left-hand side. So 2x squared plus 11x plus 19 minus 4 is equal to 0. So 2x squared plus 11x plus 15 is equal to 0. And we're doing that because when we're solving for a quadratic equation, we want to make sure that one side of the equation is 0. And in this form, we can now factorize. So we're going to get 2x plus 5 by x plus 3 is equal to 0. Either 2x plus 5 is equal to 0. So that means that 2x is equal to minus 5. So x is equal to minus 5 over 2. And in a case like that, we can substitute x is equal to minus 5 on 2 into any one of the equations, equation 1, 2, or 3. Equation 2 looks the simplest. So let's do that. Y plus 11x is equal to 4. So we can substitute. We're going to get y plus 11 by minus 5 on 2 is equal to 4. So y minus 55 on 2 is equal to 4. So y is equal to 63 on 2. So we actually have one pair of coordinates, which gives us one point of intersection. And now, let's look at the other brackets. X plus 3, that has to be equal to 0, so x is equal to minus 3. And if we substitute x equal to minus 3, just as we did before in equation 2, we're going to get y plus 11x equal to 4. So y plus 11 times minus 3 is equal to 4. And that gives us y minus 33 is equal to 4, so y is equal to 37. So the 2 points of intersection are minus 5 on 2, 63 on 2, and minus 3, 37. Part D. An employee of a company is offered an annual starting salary of $36,000, which increases by $2,400 per annum. So there's a constant increase. Determine the annual salary that the employee should receive in the 9th year. So we know in the first year, which is t to the 1, or A, is equal to 36,000. And every year it increases by a constant amount. So the common difference is 2,400. So they're asking us to find the annual salary in the 9th year. So t to the n is equal to a plus n minus 1d, which is a formula that's given in the formula sheet. So let's substitute for when n is 9. It's going to give us 36,000 plus 9 minus 1 by 2,400. Because n is 9. And that works out to be $45,200. So that will be the employee's annual salary in the 9th year. May 2016, number 1a. Domain for the function f of x is equal to 2x minus 5 for values minus 2, minus 1, 0, and 1. So let's bring up the domain in a dark gray oval and plug in those values. Determine the range of the function. So how do we go from minus 2 to give us our range value. So we can plot a little table, x minus 2 minus 1, 0, 1, and our function is 2x minus 5. So let's substitute 2 times minus 2 minus 5, which gives us minus 9. 2 times minus 1 minus 5 is minus 7, and continuing will give us minus 5 and minus 3. As such, minus 2 is plotted to minus 9, minus 1 goes to minus 7, 0 goes to minus 5, and 1 goes to minus 3. So the range is minus 9, minus 7, minus 5, minus 3. Part 2. Find f inverse x. So if f of x is equal to 2x minus 5, let's make x the subject of the formula. So it will be f of x plus 5 is equal to 2x. So x is equal to f of x plus 5 all over 2. And we're going to write it as inverse now. So we change x to f inverse x is equal to, and we change f of x to x plus 5 all over 2. Part 3. Sketch the graphs of f of x and f inverse x on the same axes. So if we look at our first graph, f of x, we can see 2x minus 5 is cutting at minus 5 in our blue line. And then when we include f inverse x, that's our red line, and they intersect at 5, 5. And if we want to comment on the relationship between the two graphs, you can see a dotted line here which tells us that that is a mirror line. So f of x and f inverse x are a reflection of each other about the mirror line y is equal to x. May 2016, number 1b. Solve the equation 2 to the index 2x plus 1 plus 5 times 2 to the x minus 3 is equal to 0. This is a reducible equation. So we want to get it into the form of 2 to the x. So let's manipulate it. We can split up 2 to the power 2x plus 1 into 2 to the power 1 times 2 to the power 2x plus 5 times 2 to the power x minus 3 is equal to 0. And we know 2 to the power 1 is 2. And we can use the laws of indices and split up 2x. So we can say 2 to the power x in brackets squared plus 5 times 2 to the power x minus 3 is equal to 0. So we have the same brackets, so let's substitute for that. So let p is equal to 2 to the power x. So the equation now becomes 2p squared plus 5p minus 3 is equal to 0. So we've simplified the equation. It now looks like a simple quadratic. And we can solve for that. And that will give us 2p minus 1 times p plus 3 is equal to 0. Either 2p minus 1 is equal to 0, which means 2p is equal to 1. So p is equal to a half. And we can substitute for that because we know p is equal to 2 to the power x. So 2 to the power x is equal to a half, which is 2 to the power minus 1. So we can equate the index. So x is equal to minus 1. Or p plus 3 is equal to 0. So p is equal to minus 3, which means 2 to the power x is equal to minus 3. And 2 to any power will not give us a negative. So this is not possible. As such, the only answer is x is equal to minus 1. Part C. Part 1. Given that t is equal to k p to the power h on c, make c the subject of the formula. So let's rewrite the equation. T is equal to k p to the index h over c. And first thing we can do is move the k across. K is multiplying on the right side. When we bring it across, it will be dividing. Or we can write it as t times k to the power minus 1 is equal to p to the power h over c. Remember, we're trying to make c subject to the formula, so we want to remove the p from the right hand side. So we can use logarithms. So we can say log t k to the minus 1 to the base p is equal to h over c. Remember the logarithm law where we have log a b is equal to log a plus log b. So we could split this as well. So we get log t to base p plus log k to the power minus 1 to base p is equal to h over c. And if we have k to the power minus 1, simplify that using the law where log a to the power n is equal to n log a. So we get log t to base p and bring the minus 1 in front. So it will give us minus log k to base p is equal to h over c. So if you want to find for c, c is on the denominator on the right hand side, we could bring it across. It would be in the numerator on the left side. So we get c times log t to base p minus log k to base p is equal to h. So if I want c alone, then we can take that on the left hand side, the brackets, and move it across to the right side as a denominator. So c is equal to h over log t to base p minus log k to base p. C part 2. Solve the equation log x plus 1 plus log x minus 1 is equal to 2 log x plus 2. So let's rewrite it. If we have log a plus log b, we can rewrite it as log ab. So the left hand side can be written log x plus 1 times log x minus 1. Both of those terms are to base 10, so they can be combined, and base 10 is understood, so there's no need to be written. And on the right hand side, n log a can be written as log a to the index n. So we can rewrite the right hand side, so it'll look like log x plus 2 squared. We're carrying the 2 from in front and making it the index of x plus 2. And since both sides are logs, we can remove the logs. So that will mean x plus 1 by x minus 1 is equal to x plus 2 all squared. And we can expand the brackets and simplify to solve for x. So x plus 1 by x minus 1 is x squared minus 1. And on the right hand side will give us x squared plus 4x plus 4. So if we bring everything across, we're going to get x squared minus 4x minus 1 minus 4 is equal to 0. And the x squares cancel. So we're left with minus 4x is equal to minus 5. So minus 4x is equal to 5 when we carry it across. So x is equal to minus 5 over 4. So only when x is equal to minus 5 over 4 and we substitute it into the equation up on top, then the left hand side will work out to be the right hand side. May 2016, number 2a, part 1. Determine the nature of the roots of the quadratic equation 2x squared plus 3x minus 9 is equal to 0. So what we want to find out is whether or not the quadratic equation has two real distinct roots, two same roots, or unreal roots. So a is equal to 2, b is equal to 3, and c is equal to minus 9, the coefficients. And the discriminant is equal to b squared minus 4ac. And if you look at the quadratic formula given in the formula sheet, the discriminant is what the square root is under. So if we substitute for there, we're going to get 3 squared minus 4 times 2 times minus 9. And that answer works out to be greater than 0. As long as the discriminant is greater than 0, it means that they have two real distinct roots. Part 2. Given that f of x is equal to 2x squared plus 3x minus 9, sketch the graph of the quadratic function clearly indicating the minimum value. So we can convert this quadratic into a perfect square, and by completing the square, we'll be able to identify the minimum values, which we've done previously in this video, but let's use a different method. If we know f of x is equal to 2x squared plus 3x minus 9, we should be able to find out the roots of the quadratic equation. So let f of x equal to 0. So 0 is equal to 2x squared plus 3x minus 9, and we can factorize or use our quadratic formula. So we're going to get 2x minus 3 by x plus 3. So either 2x minus 3 is equal to 0, so 2x is equal to 3. As such, x is equal to 3 over 2, that's one root. Or x plus 3 is equal to 0, so x is equal to minus 3. That's the second root. And since we know that quadratic equations are parabolas, it means that there's a line of symmetry or a mirror line. And that line will pass through its minimum or maximum point. In this case, the coefficient of x squared is positive, so it's a U-shaped graph. So it means it's passing through its minimum point. So we can use the idea that the minimum point, the x value, lies directly in the middle of the two roots. So if we find the average of the roots, then we should be able to find the x value for the minimum point. So the minimum point, x value is equal to minus 3, that's one root, plus 3 on 2, that's the other root, divided by 2. We're finding the average. And that works out to be minus 3/4. So when x is equal to minus 3/4, that is where the minimum point lies. or the line of symmetry, or the mirror line, or the axis of symmetry. And if we want to find the y value, we can substitute x is equal to minus 3/4 into f of x. So let's write the formula. F of x equal to 2x squared plus 3x minus 9. And f of minus 3/4 would be equal to 2 times minus 3/4 squared, which is 9 on 16 times 2, which is 9 on 8, plus 3 times minus 3 on 4, which is minus 9 on 4, minus 9. So f of x is equal to minus 10 on 1/8. So if we bring up our sketch here, if we're using completing the square method, we just needed to identify the minimum point, which is at the base, which is x is equal to minus 3/4 or minus 0.75, and the y value would be minus 10.125 or minus 10 and 1/8. But in our method, we were able to also find the two roots at minus 3 and 3 over 2 or 1.5. And we can see from the original equation, 2x squared plus 3x minus 9, c value, where the value at which it cuts the y-axis, is minus 9. May 2016, number 2b. Evaluate the sum of terms from 1 to 25, or the first 25 terms of 3 to the power minus n. So t to the 1 is equal to 3 to the minus 1, which is 1/3, and t to the 2, or the second term, is 3 to the power minus 2, or 1 over 3 squared, and t to the 3 is equal to 3 to the power minus 3, which is equal to 1 over 3 cubed. And we're doing this to be able to identify whether or not this is an AP or a GP. So if we're moving from 1/3 to 1/9, which is 1 over 3 squared, to 1 to the 27th, so if we say T2 over T1, that'll be 1 over 3 squared, or 1/9, divided by 1/3, and that works out to be 1/3. Try T3 over T2, we're going to get 1 over 3 cubed divided by 1 over 3 squared, and it's still going to give us 1/3. As such, the common ratio between the terms is 1/3. So this works like a geometric progression. So if we want to sum the first 25 terms of a geometric progression, then we have a formula which is given in the formula sheet. S to the n is equal to a, r to the n minus 1 over r minus 1. So the sum from 1 to 25 of 3 to the minus n is equal to, we can substitute a is the first term, which is 1/3, times r is 1/3 to the power 25 minus 1 all over 1/3 minus 1. And 1/3 to the power 25 is extremely small, it tends to 0. So we can say the brackets works out to be minus 1. So we'll have 1/3 times minus 1 over minus 2/3. And that works out, and you can use a calculator, and that gives us a half. So the summation for the first 25 terms of 3 to the minus n is approximately a half. Part C. A man invested X dollars in a company in January 2010, on which he earns quarterly dividends. At the end of the second, third, and fourth quarters in 2011, he earned $100, $115, and $130, a constant increase. Calculate the total dividends on his investment by the end of 2016. T to the 1 is equal to x, as given. The seventh term, t to the 7, is equal to 100, which is at the end of the second quarter of 2011. The eighth term is 115, the ninth term is 130. And if we say the ninth term minus the eighth term, that's 130 minus 115, that gives 15. And the eighth term minus the seventh term is 115 minus 100, which is 15 as well. So we're finding a common difference between the terms, represented by D, as equal to 15. And we have a general formula, which is given in the formula sheet. T to the n is equal to a plus n minus 1d. And if we substitute for the seventh term, which we know works out to be 100, that will be x plus 7 minus 1 times 15 is equal to 100. So we can solve for x. 7 minus 1 is 6, 6 times 15 is 90, and we carry it across, 100 minus 90, so x works out to be 10. So now we want to find the total dividends at the end of 2016. We know the formula S to the n is equal to n on 2 by 2a plus n minus 1d, and that's also given in the formula sheet, the sum of an AP. And the end of 2016 will be the 29th term. SC29 is equal to 29 over 2 multiplied by 2 times 10, because A is 10, or X, which we just worked out, plus 29 minus 1 times 15. So the sum 6,380. So that would be the total dividends that the man invested that he receives at the end of 2016. We've now come to the end of CSEC past paper questions in section 1, Algebra, Sequences and Series, in the subject of Additional Mathematics. We've completed past paper questions from 2012 until 2016 for 5 years in this section, and our next video will be from 2017 until 2022. Don't forget to look at the description down below, where we have outlined the playlists for you to follow in order to get a better grasp of what's happening in additional mathematics.